Okay, so welcome back to the second day of the ARCHER2 HIP programming course. The plan for today is I'm going to do a brief review of some key concepts we discussed yesterday, because I think it's really important to try and a bit more about the programming model before some of the topics we do today. So it'll take 5 to 10 minutes to do that. We'll then look at the solution for the example yesterday. Actually, before I start going, Jaffrey, can you hear me okay? Is this coming through?
Yes, James. Yeah.
Great. So we'll just review those concepts quickly, just to make sure everyone's reminded of them, because they are quite important for today. We will then look at the example from yesterday and how to approach that. And then I'll start talking about how we can look at writing our own kernels. So yesterday we focused on some key concepts and some bits about data movement. And then today we're going to look at how we actually do useful work on a GPU. How do we launch execution on a GPU? So initially we'll have a more simple example for the sort of first exercise. I'll talk about some of the design considerations for that, and about the syntax, and we'll do that. We'll then take a break at about sort of 10:45. We'll then come back and I'll look at the results of that, and then we'll kick off a more complex example of launching a kernel, and we'll also look a little bit how we can look at performance as well, and how we might be able to extract information around performance. And that will take us to the end of today. So without further ado, let me get screen shared. Okay. So these slides are just the slides that are on the GitHub pages, same as yesterday. I should also paste in the link again. This is the Etherpad. If you have questions, you can paste them there and I can look at them asynchronously if we don't get a chance to answer them in the session. Yeah, okay. So a lot of yesterday's talked about introducing the key concepts behind GPUs and why we're going to get performance from using very large GPU systems. The HIP or CUDA programming model, which we tend to refer to as the kernel-based programming model, we really shouldn't have to worry about how the device arranges the cores and memory in order to use and operate our particular function calls. We haven't really talked about running operations yet. We're talking about moving data mainly. But the key aspect of this is how we decompose problems into threads. If we have a one-dimensional problem, we can decompose this into an array. We can assign individual elements to different threads. So this is different stream processors on the AMD side or CUDA cores. Each thread is going to get each core is going to get a different piece of data to do work on. It's going to do the same instruction, but a different bit of data to do the operation on. So therefore, this has to be independent work. The execution flow can't depend on neighboring bits of data. They need to be independent. We can extend this into work groups or blocks. So we can have a collection of work items, a collection of threads scheduled to run on a compute unit, and we're going to provide blocks in which to do this work. And we're going to decide how many threads and how many blocks we're going to want to pass to turn our particular problem into in order to pass to our compute unit or our streaming multiprocessor. And that decision, those ratios and that tuning is going to affect your performance and correctness. So you're going to have to be careful about how you make decisions around organizing this blocks and threads pattern in order to best address the hardware that's underneath on the GPU. Yeah, so a wavefront is a subset of a work group. So it's designed to execute a single instruction on a set of threads. Remember, threads all work together in groups. In AMD's case, 64. On NVIDIA, it's been 32. And we are going to pass blocks of work to compute units, and then they're going to execute through that work in groups of wavefronts. Yes, the problem size usually dictates the number of wavefronts per work group, things like this. So these ratios are all going to be important to our performance later. We can naturally extend this to 2 dimensions and even 3 dimensions. This is called the grid. So we have a arrangement of work groups in a 1, 2, 3 dimensional space. It's still the grid, just to have what dimensionality that grid has. And this can get more complex, and now you have to worry about which is really the fastest moving index and where, how are you going to access the memory effectively in this 2D picture, so that each of the threads is accessing strided memory. And we'll come on to that, what that really means in a minute. Okay, so that's the real bit I think I wanted to go over. Just trying to check if there's nothing else in particular that we missed. Talked about compilation yesterday, so I won't review this. The key thing is around how we're going to access our problem and how we're going to pass the data into each of the different threads of execution on the GPU is going to be really important to us today. So I just wanted to go over that sort of picture again, so especially everyone's mind. Okay. So with that said, how did everyone get on with the exercise from yesterday? Does anyone have questions before I sort of look at their results? Is there any particular aspect that we found challenging? Any comments on that? Good, that's success, fantastic, okay. Okay, does anyone want me to go through that, or are you happy for us to move on? If someone would find it valuable for me to step through that quickly, I'm more than happy to. Great, okay, fantastic. Okay. In that case, we'll move on to the next section, so we've got some more time to try stuff out. Through these sessions, so let me just switch to the next deck of slides then. Oh, actually, there was one point I wanted to make here, actually. Let me just go on to that last page. So one other thing to kind of sort of whet your appetite for later in the course a little bit is that there's many different types of, there's more than simply host to device and device to host in terms of the way you can copy data. Okay. So this bit down here, we've set some size, but we could also move data in different ways. Is this going to show this screen? It is, okay. So if we look at, oh, I thought this took us straight to the correct thing. If we look at the documentation, we can find it was that's what I wanted to hit mem client link. Okay. You also have other types of memory copy, so you can dictate that it isn't just host to, you could have host to host copy, you could have host device and host device to host that we've seen. You can also have device to device as well. You can also have some form of default as well. So there's more complex structure you can use in these type of copies. So while we've really focused on this host to device picture, the same functionality to be used to do more complicated things in the future. When would you need a host-to-host copy for the HIP API? If you wanted to why would I want to do that? If I wanted to, I could have 2 processors, I could have 2 memory regions on a host. I could just do just a memory copy regardless. It depends who's managing my memory. If I've got, this is something that will come on the beginning of the next session, I might want to explicitly tell HIP, who may own the memory, even though it's host side memory, that I'm moving it around. Does HIP device-to-device copy allow for copying of different devices without transferring back to the host? Yes. Okay. So yesterday I had a diagram. I'm not sure if it's in the. Let me see if I can find the slide quickly. Where we had this diagram of a GPU node. Here it is. Okay. I'll just do the Jackie share my screen thing for a moment to show you this. Okay. Is that going through yet? Yes, okay. So on this picture, you can see you've got these red links, which are sort of host to device or host as the CPU out to the network links. You also have these blue links between the GPUs. The device to device copy, if it's operating correctly, will not make a copy on the CPU first and then go back to another device. It will go straight between the devices. And this is an important performance improvement between generations of GPUs. This is sort of the advent of NVLink in NVIDIA's parlance. And making sure you have the right setup to take advantage of this requires usually your GPU the people providing this, I want to say HPC center, but you don't just find GPUs and HPC. The person managing the devices will hopefully have set the right flags. It's related to sort of how the copying mechanism, and if it's enabled, it will do direct transfers. If it isn't, it may do an intermediate step onto the CPU first. Okay, that's a good question. Yeah, it's important for performance more generally. Okay. With that said, let's start talking about kernels. Would host-to-host work if you wanted to copy between different nodes? Probably not, because you're transferring process, and that's the key distinction. This is a copy between the same process, so usually on the same device. Otherwise, you'd need some form of MPI call to get communication between processes. Okay. Right, kernels. Okay, so I'm going to talk for about 10 or so minutes, and then we're going to spend some time looking at practical related to this. So what do we mean by a kernel? So many scientific applications, a large fraction of the computational effort exists within discrete sections of code. Otherwise, these are what's known as kernels. So usually you have some deep set of nested for loops. Right in the middle of them, you have some form of important operation, which is being done on every single site or over the whole volume or the search space or something. The thing that's repeated the most often, that's usually your kernel. That's being done in parallel, or it's being operated on serially, and it's very slow because it's doing it thousands and thousands of times. This is where you should consider the first place to do offloading to the GPU is these kernels, where you can use the parallelism available by GPUs. You may have enough operations of these kernels in order to have thousands of threads operate them on to those operations simultaneously, opposed to one after the other. Okay. Might give you a significant benefit. So as I said, these kernels are often associated with loops and have independent iterations that can be distributed across and run in parallel. Okay, we're really focusing on areas we can parallelize. Okay, a simple example that we're going to look at initially might just be this loop that's going to tell you the index in the loop and double it, then put it into a result. Okay, there's no dependency between each iteration of the loop. The result of I equals 0 is not and isn't dependent on I equals 1 or vice versa. So these can all happen at the same time. We can therefore run the iterations in parallel, and here this can be done by defining a kernel that replicates the body of the loop. Okay, so this is my kernel. This is a function that's going to run on the GPU. What the body of it is. So this is the entry point for GPU execution. Is this underscore global? This execution space qualifier. It tells the compiler to identify where things should be running on the GPU. And then we have this concept of some special variables, which are thread index .x in this example. So this is why I wanted to show that picture previously, to give you an example of visualization, of how we should start thinking about the distribution of work in the GPU between these threads over a number of elements. So now, instead of the body of the for loop, I've got some thread index. So each iteration is going to run on a different thread. Okay. So that's the previous slide was the definition of the kernel. How do I call the kernel? We need some code that launches this kernel on the GPU. Okay, and this is this special, this sort of call to the kernel function with these triple angled brackets notation. And we have two more elements here as well. We have blocks and we have threads per block. And this is where this can get a little bit confusing. So it's quite important to go back and look at that diagram if this gets, that I showed earlier, if it's starting to get a bit squiffy. What we're saying here in the simplistic case is that we're going to have a single block, and we're going to say our problem is small enough to fit into, well, we're going to say that there's just a thread that's going to put every single element in the array. This won't necessarily be very efficient, but it means I've got a single block and I'm going to pass it around. And then I'm going to specify enough threads to run over the full length of the array. Here the array is the size of the for loop. So this is array length, so the limit of whatever the result, size of result will be. It's over I. It's the same that we're using here, array length. Then to launch, we need to pass this, and then this dim3 is just a structure which has 3 elements. This is 3 numbers, okay, to be passed in, so that we know if we're going to progress to multiple dimensions, we worry about the other 2 elements. Okay. Yeah. So the problems for this problem size, array length, which must match the total number of threads, specifies it's 1 times the array length that's being used in threads per block. And we only have 1 block. Yeah, so this is the type for the structure. We have called dim3. It's 3 unsigned integers. Okay, and the HIP library provides this definition for you. You can then have more than 1 block. So we can start to scale up further and say, now I'm going to have multiple blocks to execute over my threads. This helps to divide up the work so that different compute units can execute different blocks, and we can now start to take advantage of the greater level of parallelism on the GPU. To do this, we're going to now have a block index, so which block am I on, and the size of the block, so that I can work out and then thread index X is which thread am I within a block. So I still have I, which is my thread number, and you can, this kind of naturally follows where if I have the block, the number of blocks that I've been, the size of each of those blocks, plus whichever thread index I am in the current block gives me the total thread location I am throughout the whole problem, which means each thread is self-independent, and that means that just calling a result on I and it's still the same as expanding that for loop. I've just provided myself more flexibility about where the GPU is going to run these different blocks of work instead of putting them all into a large number of threads. Okay, this slightly complicates the threads per block, blocks that we had. So here we just, the notation below is a little bit cute, but here I've got dim3 blocks and dim3 threads per block. And in this notation down here, I'm now just accessing the X element of that, the first element. I'm updating that from what we had above. So now, instead of threads per block being the array length, it's now just a parameter we can tune. And usually this is something like 128 to 56 kind of size. It's pretty common. And you can tune this to get better or worse performance, and you can tune this for your particular application to test what gives you the best results. We then work out the number of blocks by dividing the array length by the threads per block. There's an assumption here that the problem size, the array length, is doesn't have some form. This division doesn't have a remainder, and everything neatly fits within this number of. Sorry, array length is divisible by threads per block. That's what I should say. Again, and then we just launch the same in the same way as we did before, providing blocks and threads per block to the kernel launch. That's going to execute on the GPU. Let's get the question. Is threads per block always a power of 2? Ideally, yes, because you are trying to neatly fit these into wavefronts or warps on the GPU hardware, which are 32 or 64 in length. So what you want is to assign a block with a number of threads, which is divisible by, so say it's 128. That's the block that's going to be passed to a particular compute unit. A particular compute unit is then going to do wavefronts, divide that up into wavefronts which are going to execute on the compute unit, which are going to be groups of 32 bits of data, which are going to execute. So ideally, you want that all to match up nicely, so you haven't got trailing threads. You may have something at the end of the global problem, but you don't need to divide all the blocks up to have a weird sort of overhangs, because what you're going to do is waste some threads in every single block if you don't have them be divisible by this sort of wavefront size in effect. So it's kind of a performance consideration, but there'll be an opportunity to test this out and look at the performance if you made these sort of decisions in a minute, or after this particular example. Okay, yeah, choose a number of threads with the power of 2, and set the number of blocks sufficient for the problem space. So there are a number of internal variables available by the HIP runtime that can be used in a kernel to locate a given thread's position within the overall grid. So you have a grid dimension, which is the total number of blocks in each of the dimensions. You have block dimension, which is the total number of threads per block in each of the dimensions. You have block index, which runs from 0 up to the total. You have block index, which runs from the 0 up to the grid index. Okay, so are these kernels equivalent to function blocks on host? I couldn't get the flow of how kernel fits into HIP. They are just functions which are defined, but they are not host executable code. They are device executable code. So we are going to we're defining. We have to define them in either they can live in their own separate file, which has to be included into our main function. So I'll end in a .hip file or .q file in CUDA, or we can have them in the main code block. And then when the compiler does a parse, it will compile this device code separately from the host side code. And what you're doing is you're launching this, and that is the operation that's going to execute on the device. Okay. And what's really being picked up is this, and then you're launching it, is the angle brackets, which are the launch process for this particular section of code. Okay, we'll come on to a little bit more about launching in a second. So as I was saying, we have different parameters that are available to identify the threads that we're executing on throughout this within the kernel. This is the device side code that's going to be run on the GPU. So these names should be considered reserved, as in you shouldn't be trying to use them unless for their intended purposes. Okay, we now have the question of synchronization. Okay, so we've defined a kernel, very simplistic one. We've launched a kernel with this call to my kernel with these triple angle brackets, and we've provided how we would divide the workup over the available threads and blocks on the device. However, this function returns immediately. Okay, that execution is going to happen asynchronously on the device. Depending what's queued up before it, there will be some order occurring, but we are returned, and the CPU side, host side, will continue execution flow independent of what's happening on the device. Okay, unless we synchronize by using HIP device synchronize, for example. So we can say, right, stop at this point until everything is complete up to this location, and then we're going to continue. So we don't know that that kernel has been completed unless we run a synchronization call. So I could do other useful work here. I could return immediately, and I could do a load of other unrelated work that don't care on the results of this particular kernel. And that would allow me to get the host to do work while the device is doing work at the same time. So the question, is synchronization similar to an MPI barrier? Yes, you can think of it as like an MPI barrier. It's, there are different layers of synchronization, but this is device synchronized, so this will be everything on the GPU that's currently selected. It won't be global. Yes, you can choose which device to synchronize on in a multi-GPU system. You can also decide with certain systems within a GPU where to synchronize as well. This will be covered by later sessions in more detail. But you have a lot of control about how you decide to stop. And this allows you to design more complex systems where you can, as the programmer, make decisions about what can happen in parallel here. So the idea here is that you can use the GPU to do a lot of work, and on the host you could be doing other things at the same time, making sure you're fully utilizing all the processing elements within your system. Okay. But the key thing here is for those who have not got experience with these sort of synchronization problems is that you cannot rely on the data from or the results from my kernel having completed until you've synchronized at some point. There's no guarantee that that kernel will have actually executed on the device. Okay, so we talked a little about error handling last time. Here, we need to think about it a bit more as well. So errors occurring in the kernel execution are also asynchronous. This can cause quite a lot of confusion. We'll quite often see the assert. So before we have this HIP assert, it's going to go check the result of a HIP call and give us some information around if there was an error. It will check against success effectively. The kernel is a function you've defined which doesn't have a return statement. Okay, it does not return an error directly. So what you have to do is call some helper functions which are going to go peek at the last error. So if there's an error within your kernel, you can peek at it and see what was last put on the device. But it won't provide an error directly to you or return an error to HIP assert itself. So you have to go and do this peek. And then we might synchronize after this. Now we've completed that kernel. Okay. Yeah. So it queries the error. So HIP peek at last error, queries the error state without altering it, and will fail if there's an error in the kernel. So this is if the GPU is not available, or more likely there's some error in the way you've configured the launch of the kernel. Yeah, so if there's errors occur during the execution of the kernel itself, they won't appear until after the device synchronize. These are due to program error, which require debugging. Yeah, pretty much. So you're going to get some form of launch error, and then you're going to get some more detail about the actual details of the kernel execution itself. So we talked about this kind of fancy triple bracket setup for launching kernels. This is really just kind of a mask over a slightly more complicated function call. It's a nice bit of syntax, but it's a compact bit of syntax. That's probably a better way to put it. But there are other options. You can just call this HIP launch kernel GGL macro. And you can provide all the parameters into there. So you can provide a function pointer and then the blocks and threads, along with any other information around. Other arguments will come on to in more detail later. So the kernel function, yes, I've just described all those bits. So an example at the bottom, if we have something called my kernel, it might look like HIP launch kernel GGL, my kernel being the function that's going to get called, blocks, threads per block, and we're just going to have some form of, and then we're going to have some other parameters that we're going to set for 0 for now, and then the result is the argument of the function my kernel. So I would have I could have a longer list of arguments if I had a more complex set of arguments to my kernel. Okay, this is, you'll see this less often, but you should be aware that this is another option for launching up kernels if you prefer. Okay, so that's enough of me talking so far. So what we'll do is we will spend sort of 30 minutes looking at this, and we'll take a short break for 15 minutes, and then I'll come back and look at the result. So log on to ARCHER2. Don't forget to load the modules we needed to load yesterday to get everything set up so you have the right compilation environment for ARCHER2. You can either start from the solution from the previous exercise, or there is another code snippet or example program which has done that bit for you. Basically, what you want to be doing is you want to example a bit more detail here. Yeah, so you want to write your own kernel, apply some scaling to this, make sure the operation performs on each element of the array, and get it to print back the results. Be careful about making sure the data is in the correct place, that you get the data back into the right place, that you're checking for errors, and the kernel makes sense. You've got a function prototype, and try out different ways of setting threads and blocks and try to understand if you're doing that correctly. Okay, so yeah, so we're going to spend the next sort of 30 to 40 minutes looking at this example. Ask any questions you have in the chat. I mean, Jeffrey will be here to help you answer anything you have as you do this. just going to post the link to the GitHub repository again for those who have not got it in. And in the chat, I've put the set of modules you'll need to load on ARCHER2 to make sure you've got the right environment for compilation. And there's the default compile line. You'll need to change what you're compiling as well. Yeah, there's 4 sections to this example, so I'm just going to show this initial one on the screen so everyone can see it, but do look at sections 3 and 4 because they make it slightly more complicated by starting to introduce multiple blocks and how you might deal with cases where you don't have an array length which is perfectly divisible by the some threads per block. Okay, so the question is, in the kernel called myKernel, bracket, so the argument is result, does result refer to memory on the device or on the host? This is memory on the device. So you need to make sure that that memory already exists there. Okay, can you send me your kernel? There are debuggers that can, there are some built-in debuggers into Rockham, but I think the question will be, what data are you passing into the kernel? So what's your, and this is what's on the slide, what's your X that's going in? So can you send what your kernel call line looks like, the launch line, so the myKernel with the angle brackets bit? Yeah, okay, that's what I thought. So where does HX live? Is that a device piece of memory or a host piece of memory? Yeah. So if it's on the host and myKernel is executed on the device, the error makes a lot of sense. It's an unknown memory location because you're passing it in the location of the host memory, not the version you copied to the device. So just so I get a sense of how people are going, so there's a couple of ways we can organize it. I do want to have some time for the next example because we kind of extend these kind of principles up to higher dimensions. But what I do also want you to have a fantastic. But time to have a little bit of a break because there's I've been talking a lot and you've been counting along. Do people want me to look through some solutions now or in 5 minutes time and then have a break, or would people prefer if we had a break first, and I maybe show some solutions at kind of 5 past 11. So if you want solutions in 5 minutes, yeah, break first. Yep. Anyone else? Because if we have the break first, it will give people who want a little bit more time to work on things. That's a bit more time. Okay, great. So what we'll do then is people who want to continue working, keep going. We'll take a break and we'll come back at 5 past 11. And I will look at some solutions then for 5 minutes. Okay. Have you allocated DA on the device, and have you copied data into that location from the host?
Yeah, I'll copy the lines that I used.
You can cheat slightly. Because DA is a constant, you can just copy a constant over directly and just put a value and just call it as an int. So instead of having an int pointer to DA, you could just have an int A, for example.
Okay, we'll try that.
Okay, if everyone's back, please just put a sort of +1 in the chat, and we will get going as soon as a number of people have returned. Great, that's a lot of pinging. Okay, good. So there are a few parts of this exercise. We'll go through them in turn. For those of you, I should have said this earlier, but for those of you who've made progress with that quite quickly, there's also a slide extension of it as well. So I provided the link to these slides earlier, but there are some little stretch tasks if people have got that at the moment. So let's just review what this is actually asking us to do. So starting from our solution previous example, or there is a new case within the files, we're going to try and implement an initial kernel. I'm going to call it my kernel. We should name it something semantically relevant to a particular use case in future, but at the moment we're just going to call it my kernel. We want to scale the value of elements in an array. We want to initially limit ourselves to 1 block, and then we're going to move beyond that to multiple blocks moving forward. And then finally, so then we're going to change the array length to do that, so we've got multiple blocks to execute. And then finally, we're going to think about cases where the array size is not divisible by the threads per block. Okie dokie. All right, let me just get my terminal up and we will get going. Yes, that's what it would be. Okay. That looks broadly visible to everyone. Does anyone want that a bit larger? It's just a little bit larger. Looks good. Okay, great. I am just in a location with the files, and I've got these 2 files here. We can cat the README to get some information about what we're trying to do here. But we're going to just focus on looking inside the file to begin with. Okay. So this is the right place, and then let's just start from the top. Okay, so implement a simple operation. X equals AX for a vector X of type double and a constant A. Write a kernel of this form, which performs a relevant operation for 1 block. Okay, in the main part of the program, declare and initialize the variables for them of dimension 3 that we need to hold the number of blocks, number of threads per block, and use 1 block initially, and then we're going to extend this. Okay, so I'm just going to define my kernel. So let's just look at the code to begin with first. So we've got our error checking at the top. This is our HIP assert assistance. We're going to start with an array length of 256. We're going to, so these are just some parameters which I'm setting using the preprocessor variables. So I have array length of 256. My number of blocks is going to be 1, and my number of threads is going to be 256. So threads per block is 256. So that means my array length and my threads per block match for now. We're setting our constant A to be a double. We've got an input array, which is our hx, which is on the host. We've got an output array, hout, which is on the host, which is our output on the host. And we've got our device array, or pointed to our device array, which is going to be dx. We've got a parameter for the device number, and we've got n devices. So we're going to count the number of devices available to us, and we're going to throw an error if we've not got any devices. So we just check that we actually have a GPU to start with. And then we're going to print some information about the device itself for the system. Okay, so we're in the previous call, but just to call out what's happening. Here we're going to allocate our hx, our input array that's on the host, and allocate the output array which is on the host as well. It's just a double array of array length. We're going to assert that these are non-zero so that we actually make sure they were formed. And then we're just going to fill hx, our input, with the value of I. So this is going to go 0, 1, 2, all the way up to the 1 minus array length. Okay. So for the previous exercise, we then sort of did this bit. It's kind of here. We asserted, make sure that, sorry, what we did is we allocated dx on the device with some size. And the size has been pre-calculated here for us, so it was up, further up. Yes, so size is type size t. It's the array length times the size of a double. So this is the amount of space in memory we want allocated to fit the whole array, dx. So here we're going to allocate the memory on the device. So we have to call HIP, say allocate this memory, and I want the location of that memory to be returned to me on the host and put in the location dx. I am basically storing an address, the postal address of where this memory lives on the device so I can use it later. But I need to have it on the host because the host is controlling other operations, so it needs to be tracked on the host. Okay, and we've initialized our value hx, so we're going to use our memory copy operation to get our initialized values hx onto the device. So we're going to call HIP memcopy host to device. Remember this, the signature of this is the target location, the source location, the size of the data to be transferred, and the type of copy, the memory copy kind, which is going to be used. All the time we're doing HIP assert to make sure that these operations complete, and these are host side calls, so we know they're going to synchronize and complete when they're done. Okay, there's no asynchronous nature to these. What we are going to do in a moment is add a kernel in here to do some useful operations, but just to go back to the previous example, we will then copy the result back once we've done our operation, and the result will be contained in dx. What we're going to do is we're going to double a value in place. So we will move data from dx back to the host, but this time our target is going to be the output array h underscore out. We have the same size because they're all the same length, and also, but the kind of copying we're doing is going device to host. All right, the rest is all around us checking our results and making sure we've done the correct thing. Okay, so I've said enough there about that. So first we need to define our array. So let's do that somewhere towards the top of the file, just for simplicity. I'm going to have some global Miro. What am I doing here? Okay, indentation all wrong. I need to have some integer I, which is my, so I can iterate through, well, I'm not iterating in this case, I can go through the entire vector x. So this is just, and address each one. So this is going to be done by thread index to initially. So thread idx.x, so it's going to equal this. And I'm going to have x of I is equal to a times x of I. Okay, I'm just going to double in place. And you can see I have no return statement. This is a void function because I can't return a value on the device because it won't go anywhere. It's just going to, so I need to make sure I'm copying data, I'm editing data in place and I'm copying it back when I'm doing GPU function calls. Okay, because if I was to return data, there would be a stack frame, it would return, and that data would go beyond the device and it wouldn't go into anything because all the variables that we're talking about in this program here are on the host. So if I was to assign them, I'd need to do something different. Okay, so that's the definition of our function call, or our kernel. So I'm just going to copy the signature so I can speed myself up a little bit. And now I need to find the location which I'm going to put this in. So my kernel will be here. Okay, so now I need some, I'm missing something. I need some angle brackets. I need blocks. I need threads per block. Okay. A has been defined as we said above. And here we're going to use dx. That is the memory on the device. I need to specify my blocks and my threads per block. So this is going to be blocks. And initially we've said we're going to have one. And then I'm also going to have dim3 threads per block, which is going to equal my macro parameter, if I remember it from above, which has been set for me, which is threads per block, okay, which is equal to my array length. So slightly here, and the other dimensions is going to be 1 and 1. Okay, that's looking pretty reasonable. If I can get my signature to be nice. Now let's watch if this doesn't compile very effectively, and we do some fun debugging live. Okay, I need to make sure my environment's set up correctly, so I'm just copying over all my modules to make sure they load. Okay, loaded all modules. I'm just going to clear up the screen, and then I'm going to make sure I've got the compile line correct. That's going to be annoying because it's going to do it over multiple lines. Okay. Okay, should this be hip minus p, sorry, hip cc minus x hip, because my kernels are being defined inside this C file. Standard 11, I've got my Rockham path set. I need to add these two environment parameters. And then I need to add the final bit, which is the gen code, which is not there. It's up here. And then it's going to be x GFX. It is that. Okay, now I have an a.out file. Let's clear this up a bit. Let's get a cat r submit script just to see it. Okay, it's just going to, annoyingly, these run over multiple lines. But if we just stop there, then we can see it's going to run .a.out. So dispatch submit sh. And we can see what the queue is doing by doing sq minus me. We can see I'm pending and I'm running and I'm done. Okay, let's see if that was successful. Let's look at the Slurm file that's been output by this. Okay, so number of elements 256, and there's correct 256. So that's good. That's what we expect. Okay. In the interest of time, I'm going to jump to kind of the final, more complicated case. So we're going to do a couple of steps in one go. I'll just answer that question first. Yeah, there is a small, so the question is, why don't we have to copy over the constant A to the device? Can HIP pass over constants in the kernel? Yes, it can pass over constants to kernel. The limitation here is that that constant memory that's available on the device is very small. So it's only good for individual constants to be moved across, nothing really larger. So you can get away with it. I'm cheating slightly here. You could be more judicious and move it across via a memory copy, but you can get away with it. Okay. So okay, so outer loop, but is it necessary to have HIP assert? I've previously written dx equals HIP malloc data array, size of data. The HIP assert is protecting you to make sure that that copy completed successfully, and you know that it did. You're just trying to justify that it's actually happened. The output of HIP malloc, I'm a bit confused what the return scope of what DX is actually there. Is it really the memory address on the device, or is that just data now? How does your program know which constants it needs to move to the device, or does it move them all? It moves them during kernel launch. I think it can move a few when you call the kernel launch itself and gets the values at that point. So you have to specify. It's not going to do it just with everything in the program. Okay. Right. Let's do the more complicated case. So now we're going to move to having multiple blocks. So we're going to increase the array length to be 512, which means I'm going to need 2 blocks. Okay, I'm going to start using that parameter instead. I'm going to update my kernel. Now my kernel needs to be able to deal with multiple blocks. So I need block idx.x. And then I need the dimension, so I need block dim of black dim. I need block dim dot x. So now this stage of doing things live, you misspell stuff. So block index.x times the size of a single block plus thread index. I don't need to change anything else here because it's just going to split up the executions into different blocks. But what I do need to do now is to go and edit my imp starting parameters that I'm going to pass in. So I want multiple blocks. This is going to need to be num, I think it was num blocks above, just so that I've got a parameter that can be used globally. If I had multiple kernel launches, I want to control this in a single location potentially. If I'm running over the same data, the optimizations might be the same. The other thing I'm going to want to do is I'm going to want to, I could do num blocks, or maybe better would be array length over threads per block. Okay. That should be everything. I'm just going to remove my .out file to make sure this recompiles, and then I'm going to recompile my code. Okay. just going to remove that old slump. Actually, no, I'm going to keep that there. I'm going to sbatch that submit. Okay, and we're going to run it. We're going to check that's running. It's probably already completed. We've got two Slurm output files, so we check the Slurm ID. So this is 11378167. This one. And we see now, because we've increased the array length to 512, we've got the 512 correct elements. Okay. Final complication is to try and deal with arrays which aren't of a particular length, which is kind of uniform. So let's bump this up to 1000. Okay, and now we need to calculate more carefully which the number of blocks we're going to need. We're also going to need to make so we're going to think about this a bit carefully. So it has to be something like this is the bit of maths that you always faff about getting right. Yeah, so this is array length plus threads per block minus 1 over threads per block. You must have that many you must have one more than you think, basically, is to make sure you do the counting correctly. That's all right there. I just double check my notes. Array length plus per block minus 1 over threads per block. That. We don't need to change our blocks. We don't need to change our threads per block there. We changed the array length. What we do need to deal with, though, is what happens to a thread if it gets, in our kernel, if it gets an element which is beyond the scope of our if we don't have data. So if we end up with a block with only like partial data, but there's too many threads to deal with. So now we need to pass in an extra parameter which gives us a length, which we call this nlen. Again, we're going to pass this in as a constant now, and we're just going to add a if statement in here, which says if our parameter, is less than nlen, then we can do this execution. Otherwise, we shouldn't. This protects any threads trying to access data beyond the length of the array. It basically says if you're a thread and your total thread number is beyond the length of the array, you have no data to work on. And if you try and access data at that location, especially in just a C array, it's going to run off the end and do terrible things around operating on out of scope and overflow the stack, not overflow the stack, but invalid memory access edits. So we're going to have to protect it with this, which means we need to pass an additional value in when we launch our kernel. And we can do that very easy because that is just array length. Okay. So again, I'm going to remove my a.help file, and I'm going to recompile. And I'm going to submit the code again. And it's pending, and it's pending. That's right. Question. Yeah, yes, you could, exactly. You can calculate that differently. You just need to ensure that you cover and you don't end up with an off by one error, because you'll end up with an incomplete result. So let's look at the result of that run. 78224 is that Slurm ID. So now you can see number of elements, 1000, and correct is 1000. So we've gone over the full possible range, and the maximum of threads per block is 1000. Oh, sorry, that's set in all of the cases, but the total number of threads, we would have had 4 blocks to run, each between 56 threads. So there's 24 threads that didn't do any work there, but ultimately there's quite a lot that did. Okay, I've spent a bit too long going through that example. apologies. I will now go on to the next case. Showing that. Okay, so we've done kernels. Yeah, I wanted to go on to this. Okay. Right. But that is, so again, spend a bit of time there, but that is the prototypical example for all kernels. Okay. What we're now going to look at is the slightly more complicated case. If we start looking and trying to get performance out of these systems, what do we need to do in order to maximize performance? And then we're going to look at a more complex example. So we now have a function. It's a very simple function. A GPU program, a very simple one, which moves data from the host to the device to the GPU, and executes a kernel on that data, and then moves the result back to the host, and we get the result. In a simple case, we're just checking it. It's very simple doubling. We can run it on both host and device and compare the result. What we're doing there is taking advantage of a lot more parallelism. So instead of having a program serially do every single element in a for loop, we're going to use multiple threads to do the work, but we want to make sure we're maximizing performance. So there's a law around this, a principle around this. Oh, sorry, there's a fire alarm here. One minute, apologies for that. I know it's quite loud. We have a test every Thursday at 11:30. So what I was saying was that we have a law that basically says I need the performance of a parallel program, and here in the GPU we are very much parallel, is limited by the fraction of code that is serial. So in the GPU context, this gives rise to two concerns. One, the kernel is potentially parallel if we've written it correctly, and the host code is definitely serial. All the host and device transfers or the other calls are serial code. This may mean that additional work is required to expose parallelism and eliminate host operations in favor of operations on the GPU, on the device, which and exposing the parallelism in those operations to get work on the GPU. The way we can sort of consider this on the GPU is in terms of what's called occupancy. The GPU has many compute units that can potentially be used, and having very many blocks of work available at any one time is favorable to make sure that those units of execution are filled and have work to do. So, and that's what we call high occupancy. So we want to generate lots of blocks of work so the compute units can stay busy, and we get that's high occupancy in our GPU. So that's achieved by having a high degree of what's called thread parallelism. Typically, a GPU wants 10 to the 5 threads to be available. Threads of work to be available to be efficient. So we said we had around 6,500 CUDA cores, HIP stream processors or physical cores within all the compute units on the GPUs we're looking at. And 10 to the 5 threads of execution, bits of work to do on this cause is far beyond that in order to make sure there's always stuff available to do. So when the thread finishes executing, it's got more work to come and get at. There's little benefit from using a GPU if you cannot expose this level of parallelism. And if lots of cases, you should not use a GPU if you cannot. Okay, you're not going to get the benefit from it. You see lots and lots of people go, our GPU is inherently faster, I should use GPU. It's only faster if you can really expose the parallelism. Okay, so let's consider a two-dimensional loop now. We've looked at the 1D case, let's look at a 2D case. If we parallelize the inner loop only, so each of these loops are over 512 elements, we'd have at most 512 threads of work to do. Okay. And that would be 2 blocks if there's 256 threads per block. This would be quite poor occupancy if we've got 6,000 threads available, 6,000 cores available, sorry. If we parallelize both loops, then we would have 512 times 512 threads, available. That's much better. That's 1,000 blocks of work to do. So we can use many more compute units to do operation. We could drive very high occupancy, and we'd get efficient use of our GPU. So on GPUs, many cores need to be occupied or given work at the same time to avoid underexploiting the device's resources. This means we need to optimize the memory access patterns for the GPU, and those patterns are not the same between the CPU and the GPU. We have to do something different for a GPU. This is around, we were saying yesterday when we talked about hardware, the GPUs have much higher memory bandwidth available from their RAM, but we need to program in a way that maximizes that. Okay, so what's the fundamental difference here? So CPUs like caching, they have lots of this hierarchy of caches, and the idea here, the best way to exploit this is that a thread in the CPU code favors consecutive memory accesses. So this thread is going to get element 0, 1, 2, 3, all the way up, okay? And we're going to smooth the stream of data coming in to that thread by having a hierarchy of cache which allows data to move in. Okay. That means in this double nested loop, the rightmost index, okay, is moving fastest, and that's accessing consecutive memory addresses for one thread of execution. In a GPU, we prefer coalesced behavior. Okay, what this means is that we need to have a wave front, a group of streaming processors or CUDA cores which are working together. So each neighboring thread should get neighboring memory access. So I'm going to load 32 elements together, and 32 neighboring cores are going to work on them at the same time. So we need to organize our memory access in order to enable that. So in our one-dimensional case, there's no real issue. We've got consecutive threads, we've got consecutive indexes, and they're going to access memory from A input, put it in A output. Okay, pretty simple. In the 2D case, so when we're trying to deal with a two-dimensional loop, this is more complicated. The code below initializes I in the X direction and then iterates over in the inner loop, it's iterating over Y. This means each thread now has to go all the way over J elements. J is the consecutively accessing memory. So what this means is our neighboring threads in our GPU are, I'm accessing thread 0 is accessing an element of data 0 in an array all the way up to nj, and then thread 1 is accessing ny minus 1, 0 is accessing, sorry, let me start that again to make sure it's absolutely accurate. Our processor, our stream processor, our CUDA core 0 is accessing data to do operation from 0 up to ny minus 1. Its neighbor, thread 1, CUDA core 1, is accessing data ny up to ny minus 1. Okay, that's not neighboring access of data. Okay, and the cache and the memory access pattern of GPUs does not favor that. That's not coalesced access. So we have to think about how we structure our indexing and our blocks and thread access in order to maximize this. So an alternative way to do this maximizing, is to be changed what we're deeming to be block index and thread indexes. So here, instead, we say X is going to be the thread indexes for X is actually going to be equal to Y, is equal to J. That's the fastest moving thread. That means, so what we're actually doing here is we're iterating on the inner loop. We're replacing this inner loop first, and we're leaving the outer loop over X. And this means this rightmost index, which is moving fastest, is now getting consecutive threads having consecutive access to data members in the array. This is kind of complex to understand, and it's best done through an example. So for the last 20 minutes of today, and I will make sure that Juan, who will take the next session next week, will look at this before he starts moving on, because I doubt we'll have time to look at particular solutions today. Is to try and implement this. Okay, so there's an exercise to do a simple matrix operation, which is we're going to form a matrix MA. So this is a grid with 2 dimensions with elements in it from 2 vectors, xi and xy and yi and yj. There's some constant alpha. So A is an m times n matrix, x is a vector of length n, y is a vector of length n, and alpha is some constant. We're going to adopt a flattened one-dimensional indexing for the matrix A, and that's provided in the file. And you're going to have to implement a kernel and to do this operation. As you're doing this, the submit script that's provided, so the compilation should be the same. You need to make sure you're loading the same modules and everything. You're now going to have a go at trying to extend what we've just done on a single dimension over 2 dimensions. As you do this, you can, the submit script has the Rock'em profile set up, and it will give you a file called results.stats.json. Will be outputted when you run this. Okay, and you can get the timings for the kernel out, so you can start to assess whether your changes are giving you better or worse performance as you go. And you can basically try to implement this setup, but you're going to slowly get rid of this. This is just basically saying serialize everything. Thread 0 is going to do it. If you're not thread 0, you're going to waste your time and do nothing. And what you want to do in this exercise is slowly remove these loops so that this is just some set of thread block IDs which cover both x and y dimensions, and there's no for loops here, and you have a single line which is going to update and create the matrix. And you should see as you go that you're going to get performance improvements as you make changes. Okay, so have a go with that exercise and see how you go. What I will show you briefly just before we finish is what you can do with that profiling output as well, because it's quite nice to be able to visualize a bit about what's happening. Okay, so I know you're still working on this, but I just want to show you one quick thing before we end the session in 10 minutes time around something you can do looking at your results when you run. So I will just share my slide. Why can't I share? There you go. So if you run the submit script, it has this prof thing in it. It may be a bit annoying because it will produce a bunch of output for you, so you can just remove it if you want. But if you use it, it produces these statistics files, so you can kind of cat results. I can spell be helpful, sysinfo, whatever, and tells you loads of things about the system, which is quite interesting, a bit like LSCPU. It also can tell you things like when calls were made, okay, and this is a bit verbose and a bit much. So instead, what you can do is if you download the JSON file, this one, results.json, okay, and you can then upload it to this web page that I'll show you now. It is results.json. This is called Perfetto. You can just open the trace file and you can load in that JSON, that results.json file. So you have to download it to your laptop or your computer and then do that. What this is great for is it can give you a timeline of all the different kernel calls which are happening on in your program that are happening on the device. So here I've got a bunch of stuff around getting system information and all this other stuff that's being called. And then some other queries about the system, but mainly here, this is what's happening on the GPU. So you might have to hit some drop downs to see some of this stuff, but you can see there's a lot of time being spent in memcopy. I mean, a lot is relative, right? This is still 200 milliseconds, the duration, but in terms of the execution time, it's quite a lot. In the actual kernel execution is 2 milliseconds. See, you can see the name is called hip launch kernel, and I've got the name of the kernel. In my case, I'm calling my kernel 4, and I've got all the parameters in. So this is that expanded version where we don't use the angle brackets. That's what's actually recorded by the profiler, what's actually being called underneath. And then at the back end, we see the results getting copied back. So memory copies going back to the device, to the host even, sorry. And we can start to inspect how long are these using, time them. So if you were to run this for your different implementations and get the profiling data and keep hold of it, you could compare how the performance changes depending on how you've implemented your kernel launch over 2 dimensions. And you will see a difference in the kernel execution time, and this would give you that information to be able to assess whether you're getting better or worse performance as you're working on this. Okay. So I'll send you the link to Profetto, because I think that's quite a useful tool to know about. That's the default page. There. Okay. Load results.json to look at timing. Yes, you'd have to SCP the JSON file down to your local machine. And then if you just go to, I'll share that screen again. Let me open up the other one. Okay, so this is what this looks like. You go open trace file, and then I go, oh, that's my results.json I loaded. So I've just copied all these down from ARCHER2 down to my local machine. I open it. Loads, and I can look and inspect details about these kernel calls. Get some more information about what's happening on the system. So what's this? This is a random fill buffer. Copy device to host, something happening on this particular process. The IDs here aren't particularly intuitive, but you can kind of get a sense that if it's a hit memory copy, that's happening somewhere on the device, kernel call somewhere on the device. This is a bunch of AMD control stuff happening here. You can inspect and understand kind of what signals are being sent and where you might be being held up. And this is HIP kernel launch specifically. If you're in, this is, so AMD doesn't have this kind of, it has this command line utility called prof to get profiling information out. It doesn't have anything sort of a nice UI or a fancy profiling tool yet. NVIDIA very much does. It has Insight Systems and Insight Compute, which are very nice tools. So if you're in CUDA-land, then I would recommend using them directly, and they're free to download. You can then inspect your results. Again, you've got to download the outputs from the HPC to your local machine to do it most of the time, but it can help you understand what's happening with your performance in detail. Okay, that's 12 o'clock. I will make sure that at the beginning of the next session that Juan takes a look at some of the solutions of that particular example. This is a little bit challenging. I have to remind myself the detail every time, so don't worry if it's a little bit challenging. It is meant to kind of make you think about this quite hard, and this break between sessions will actually be quite useful if you get the moment to look at it again with a fresh set of eyes. Have a good week, and hopefully this has been useful to attend. Thank you very much for turning up.